Let me give the short introductions about Martin. So welcome everyone. So today we have Martin. Martin completed his PhD at University of Vienna, and recently he joined at the QIT group at ICFO under Professor Antonio Assis. And today he will present a very interesting aspect of quantum information theory, and that is very deeply connected to quantum foundations. We'll talk about, you can see the simulating qubits in prepare and measure scenario and its connection with the Bell scenario. So Martin, we have 1 hour at least, and people might interact you, and I also encourage other people to interact him also in the middle. That is perfectly fine. So Martin, please, you can start.
Right. So hello everyone. So thanks for the introduction and for having me in your seminar. So I will talk about simulating qubits and prepare and measure scenarios. And again, first, if you have any questions, just feel free to interrupt me, or if there's any problem with anything, just interrupt me. All right. So let's start. So what we will consider in this talk are some simple scenarios that we consider in our everyday life, I think, in quantum information theory. For instance, a prepare and measure scenario where we have Alice and Bob, and Alice can send qubit states to Bob. He can measure them. Or a Bell scenario where Alice and Bob, they share some entanglement and can perform some local measurements on their part of the entangled state. And what we will ask if these correlations that we can achieve in these scenarios can be simulated with some classical resources, in fact, shared randomness and classical communication. And if yes, how many resources are necessary, and so on. All right, so in the first part, it's about the prepare and measure scenario, so quantum communication. In the second part, it's about Bell scenario, so entanglement. So let's start. So what we consider first is this prepare and measure scenario. What we have here is Alice and Bob, and Alice can prepare an arbitrary qubit state. So as we know, qubit states are represented on the Bloch sphere. So what we denote here is V. It's an arbitrary direction in the Bloch sphere. So she can prepare this as a qubit, send it to Bob, and he performs a measurement. In its most general form, this measurement can be a POVM. And when he does so, he gets an outcome. And this outcome, of course, in quantum theory, it can be a obeys Born's rule. All right, so this is the basic setup, and it's I would say the simplest scenario where we have some communication of a quantum system, and when we have such a quantum message, one question we can typically ask is if there is something that we can do with a quantum message that we cannot do with a classical message. And as a motivation, basically the simulation is about this. Okay, so let's start. I will start with as an introduction with a simple task. And this task is known as random access coding. Sometimes there's also different names in the literature. Sometimes it's called oblivious transfer, for instance. And I think it's a very nice example that shows that in this prepare and measure scenario, you can do something with a qubit that you cannot do with 1 bit of communication. So how does the task look like? Here you have Alice and Bob, and Alice, she receives from an external referee, for instance, 2 bits of information. So 2 bits, x1 and x2. And Bob, at the same time, he is asked to either output the first bit of Alice or the second bit of Alice. So he has to reply to the referee, and they win if they do successfully. So for instance, if Bob is asked to output the first bit of Alice and this is 0, then they win if Bob tells the referee 0, of course. Okay, now we can consider this task and check how well can Alice and Bob do if they have different resources at their disposal. So of course, if Alice is allowed to send 2 bits to Bob, then she can just send these 2 bits she got from the referee, send them to Bob, and then he has all the information he needs to perform this task. But it's a bit different if Alice, for instance, is restricted to send only 1 bit. And then what she can do, for instance, is she can send like X1, she can send her first bit. And if Bob is lucky and he's asked to read out the first bit of Alice, then like they can win perfectly. But if he's asked to read out the second bit, they get unlucky, and Bob has to guess. He has no information about this. And on average, turns out the winning probability is like 75%. So you can actually prove that this strategy is optimal, and you cannot reach more than 75%. All right, so why am I telling you this? Because like if Alice and Bob are now allowed to send 1 qubit of information, you can do better than with 1 bit. In fact, there's a strategy that can achieve 85% of winning probability. And the strategy looks as follows. So Alice, she given her input, so there are these 4 combinations, 0, 0, 0, 1, 1, 1, 1, 0. She prepares a different quantum state and sends this one to Bob. So for instance, if she has like as an input 0, 1, she would prepare, let's suppose this is the x direction, so that she would prepare up along the x direction, send this to Bob, and then given the bit he would like to like read out, either the first one or the second one, he performs the measurement either like in this direction or in the second direction. And what you can observe is if the first bit of Alice, for instance, is 0, she will prepare either like this state, the 0, 0 or the 0, 1. And if the first bit of Alice is a 1, she would prepare either this or this state. And then like by geometrical, like from a geometrical perspective, like you can see that like the measurement in this direction is highly correlated with like Alice bit being 0 or Alice bit being 1. And if you do a bit of math, or like you look at the geometry of the problem, it's not too hard to calculate that like in 85%, the outcome of Bob's measurement is actually correlated with like Alice bit being 0 or Alice bit being 1. Like for the second measurement, it's the same. So you always have this guessing probability of 85%. All right. So why am I showing you this? So now like we have this example of a task like random access coding that proves you can do something with the qubits that you cannot achieve with 1 bit of communication. This is of course very nice, but in principle we would like to go further. So you can ask, okay, can you also do something with the qubits that you cannot do with 2 bits or not with 3 bits and so on? And we would like to answer this question. And so in principle, like there's like you can have an arbitrary task. So Alice could have like an arbitrary number of inputs, and like also Bob could have an arbitrary number of inputs, and they are asked to solve a given like question, so some function of these inputs that the output should obey. And you can ask how well can you do with like 1 bit or 1 qubit or like a given number of classical bits. And what we can like show is like whatever you can achieve with 1 qubit in this scenario, like you can also achieve with like 2 bits. So like for every task you can think of, even if you have like a very clever strategy you can achieve with a qubit, like you can achieve the same correlations with 2 bits. And why is this the case? The case is it's true because it turns out, as I will show you now, that like 2 bits are like sufficient to simulate everything you can achieve with a qubit in this scenario. Okay, so that should be like the motivation for like studying this question. Like we have this like prepare and measure scenario, like where Alice can like choose an arbitrary quantum state, send this quantum state to Bob, and then he can perform an arbitrary measurement. And we are interested in like kind of how much classical communication, or can we produce the same correlation with the classical protocol that uses some like classical communication and also shared randomness. So this was a question that was already like asked a long time ago. So it's the beginning of quantum information, I would say. The first, or like one of the first papers about this question is from Serve, Chizong, Massa from 2000. And they have a protocol that like on average like communicates like an finite amount, but it has the disadvantage that in the worst case it can be an infinite amount. And one breakthrough that was made was by Ben Toner and Dave Bacon, and they proved that like all correlations you can achieve in this scenario like can be simulated with like 2 bits, as long as Bob is restricted only to projective measurements. Okay, so a few remarks are here important to make. So what we consider is like we want to simulate this scenario where like Alice is free to choose an arbitrary qubit state, so it's completely up to her choice. And like a priori, Bob does not have to know anything about what Alice would like to send him, and also the other way around. So like Bob is free to measure in an arbitrary basis, so he can choose. And Alice does not need to know what Bob is going to measure. So for instance, like there is another scenario that like, I guess some people of you might be familiar with, that is a scenario studied in the Frankel and Werner. Okay, like it's a scenario where like Bob has no freedom in choosing his measurement. So he's like fixed to one measurement. And this measurement basis is also known to Alice. And this is like in some sense easier to simulate because like there's a theorem that is called like Frankel and Werner theorem. And that shows that like everything you can achieve with a qubit can be perfectly simulated with 1 bit of communication. And also in larger dimension, everything you can achieve with a quantum D-level system can be simulated with a classical D-level system. But the situation is different if we also allow like Bob to kind of choose his measurement freely. So we don't want to assume that Alice knows already what Bob is going to measure. And then, so like still for a qubit, we can simulate, turns out we can simulate everything with 2 bits, but in higher dimensions, we don't really know how to simulate that. So it's not known if there is a simulation with a finite classical message. Okay, so just to avoid confusion, maybe like to set the stage. All right, so what or how can you like possibly simulate like a scenario like this? So one thing that always works is like if Alice, for instance, is simply allowed to tell Bob which qubit state she would like to send or which quantum state she would like to send. So she tells Bob, okay, I would like to send you like exactly this state, but if she wants to do that, like she has to kind of encode like the Bloch vectors of her state and send this information to Bob. But if you want to do that, like you have to, the problem is you have like an infinite set of possible states that Alice can send. If you want to like communicate this with a finite message, you need infinitely many. And at the same time, also Bob, he has like an infinite like set of possible measurements. So arbitrary directions in the Bloch sphere, if you consider projective measurements. So like it's difficult. Like you have an infinite set of for Alice for her states and an infinite set of Bob's measurement. So in principle, it's not. I would say it's not so clear that you can like simulate everything with a finite message. But in fact, like people found some clever trick, let's say, and this is like the protocol of like Toner and Bacon from 2003. And I will show you the protocol because I think it's actually quite, in some sense, simple and also quite elegant, I would say. So how does it work? So you have Alice and Bob, and one thing we always need is some shared randomness. So like Alice and Bob beforehand, like before the protocol starts, when they meet beforehand, they agree on some shared random vectors that are uniformly distributed on the Bloch sphere. So in this case, we could have like lambda1 and lambda2. These are two random directions in the Bloch sphere. And then lambda3 and lambda4, they are defined to be the negative of lambda1 and lambda2. And now they can start like the simulation of this prepare and measure scenario. So Alice, she can decide on which state, represented by this vector v here, she would like to send to Bob. And the protocol goes as follows. So she checks which of these like 4 vectors, 1, 2, 3, is the closest one to V, and she selects this index. So in this case, it would be lambda 4. Afterwards, like she tells Bob to use this like vector lambda 4. These are exactly like these 2 bits of communication. So like discriminating between like 4 different symbols, something 1, 2, 3, 4, requires exactly 2 bits. And what Bob is doing is he takes this vector lambda 4 and forgets about like the 3 other ones. So like he only uses lambda 4 from now on, and that's it. And he can like select his measurement. So like if it's like in a projective measurement, like these are 2 antipodal points in the Bloch sphere, plus some direction, like plus y and minus y. And what he checks if like this lambda 4 he got informed from Alice is closer to +1 or -1, and if it's then he outputs accordingly. So in this case, it's closer to -1, so he would output b equals -1. And what turns out is that like on average, so what means on average, like in this case, like the shared randomness is arranged like this, but in a different scenario, like in a different round, let's say, it can be different. And then the outcome is not -1 anymore, but could be +1. But like on average, if you average over all these like random shared randomness, you will see, or one can prove that like the statistics they obtain here is exactly the same as if like they perform the corresponding quantum protocol. So it's exactly like this expression here. It's exactly the same as if like Alice prepares her qubit state, sends it to Bob, and he performs a projective measurement. Okay, so in this sense, they get exactly the same statistics with the shared randomness in 2 bits of communication, and it perfectly simulates like the quantum scenario. So a few remarks here. So what is the secret, let's say, of this protocol, or how did they manage to come up with that? So it's interesting to look at this like distribution of this vector that Alice picks. So by construction, like she will pick something that is close to V, like it's close to the state you would actually like to send. So in this case, you can see it's quite close, but in general, of course, could be also somewhere else because like these lambdas are random, but it's very likely that she will pick something that is close to the actual quantum state you would like to send, but also with some probability it could be a bit further away, let's say. And so this distribution, it has a special name, or it plays a special role in quantum information theory. It's called the Kochen-Specker model of a qubit. And okay, I will say a bit more in a second, but in the end, it's like an ontological model, or in some sense a local hidden variable model of a qubit that kind of like determines like for every possible projective measurement if the outcome is plus or minus by simply checking if this vector that obeys this distribution is closer to plus or minus. And one can show that if you have like a vector according to this distribution, it obeys exactly like quantum statistics. All right, so a few remarks here. So like strictly speaking, the protocol I showed you is not is slightly modified from the one that Toner and Bacon have in their original work. So I think the first one who realized this, like Toner and Bacon at that time, they did not realize the connection to the Kochen-Specker model. But I think it's very valuable to realize that. And I think the first one who realized this is Alberto Montina in this work here. But also like the versions that I'm following is like from my own work here. So if you're interested, you can find it there. So, all right. So again, like the idea of this protocol is like based on this Kochen-Specker model. So if like Alice, she knows which state she would like to send, but she cannot send the state. That would be too costly. But instead, she's trying to sample to Bob like a vector that obeys exactly this statistics of the Kochen-Specker model. And if then Bob kind of outputs according to this rule by checking if it's closer to plus or -1, turns out you get exactly the same statistics as you would expect in quantum mechanics by Born's rule. And if you wonder, like, why is this the Kochen-Specker model? Does it has anything to do with Kochen-Specker contextuality? The answer is yes. For instance, if you're familiar with Kochen-Specker contextuality, you might know that if you want to prove contextuality, you need a higher dimensional system. With higher dimensions, I mean at least 3. So for a qubit, you have Kochen-Specker contextuality, but for instance, you don't have it for a qubit. And the reason is that, like, there is a non-contextual model that can deterministically assign like an outcome to every possible projective measurement. And this is exactly this one. So instead of the quantum state, you have like a vector according to a certain distribution. And this vector determines for every possible projective measurement if the outcome is plus or minus, simply by checking if it's closer to the point or to the antipodal point. All right, but this is just a side remark, in case you're curious. Also, this model is from the original paper from '67, where Kochen and Specker introduced contextuality. All right, so, but one downside of this model is that, like, it works perfectly for projective measurements, but like we have something more in quantum mechanics. And like, for instance, we have like general POVMs for qubits, also like in higher dimensions, like, yeah, okay, no, let's see. Like in qubits, we also have POVMs, and like we don't know, or like this model does not work for POVMs. So what we would like to do is, like, we would like to extend like this protocol, like also to the most general form of measurements, so to POVMs. So the question is, like, okay, like, is this a coincidence that these 2 bits are sufficient to simulate that if we restrict to projective measurements, or what happens if we have like general POVMs? And this is now connected to my own work, or it is my own work. Like, we managed to prove that also when Bob has like general POVMs, then like 2 bits are sufficient to simulate all the statistics in arbitrary qubit prepare and measure scenarios. Again, with this, we don't want to assume anything that Alice knows what Bob is going to measure, and the other way around. All right. So
Yes. Hi, Martin.
Yeah.
I have a question here. So I just forget the proof. So is it necessary also? 2-qubit is necessary also?
Yes.
You proved that, no? That 2-qubit is also necessary, right?
Yes. So what you can ask, okay, like, you have these simulations. The question is, can you also simulate it with less than 2 bits? So you can definitely not simulate it with 1 bit, because that would be a contradiction to like random access coding. If you could simulate it with 1 bit, then there would be no qubit advantage.
Yes.
But so, like, what you can also prove is that you cannot simulate it with 1/3 of communication, for instance. So like a trit is a three level classical message.
Yes.
And it turns out this is not possible.
Then only one is left, which is 2-bit.
Yes. Yes.
Okay.
But okay, what is, for instance, unknown if like something like 50% of the times you send 2 bits, 50% of the times you send 1/3. Like this, for instance, we don't know.
Ah, okay. Okay. I mean, you're saying on average, it's somehow whether it can be in between log 3-bit and log 4-bit.
Yes. Yes, exactly. So like on average,
somehow, yeah. Because somehow what is happening in case of just sending a qubit, it is a completely oblivious to Bob. But in your 2-qubit model, somehow you are sending some informations where the X is lying, whether it is upper hemisphere or lower hemisphere.
Yep.
So somehow 2-qubit is a little bit more powerful model than only 1-qubit. I mean, it is not any more oblivious.
Mm-hmm.
Just a small remark. Yeah.
Yes.
Okay.
Yeah, so it's true. Like Bob, he gained some information about the qubit state, and kind of this information, it should be like enough to produce an outcome, but it cannot be too much information about the qubit state.
It cannot be too much. Yeah.
Then it would be like the communication cost would be too high. Then Alice has to send too much information.
Yes, yes. If I in your two-qubit protocols, if I try to find out the mutual informations, it would be obviously greater than log 2, right?
So I think yes.
Because at least you can, because you are actually marking whether it is upper hemisphere or lower hemisphere. So that is actually sending one log 2 amount of informations. And then you are measuring something by 5y, and there also you can get some information about the x. So that's why it would be more than log 2, right? Whereas in case of a qubit, it cannot go log 2. It cannot go beyond log 2. Yeah. That's
so there are also some works, for instance, like if you do like many rounds in parallel, then also the communication cost can go down. Like so Alice can send many qubits like in parallel, and then like there is a connection between like the mutual information of this ontological model, of this Kochen-Specker model, and like the average communication you need in this case. So there are some works on that.
I see. Interesting. Who did that work? And okay, I will discuss later about this. Okay, thanks.
Yeah. All right. Okay. So I've been here. So yeah, like this Toner-Bacon model, it works perfectly for like projective measurements, but for POVMs, like it was not clear if you can do the same. But it turns out to be the case. And like what we kind of, so this is my own work now. And what we had to prove is, or what we had to introduce is like a new model that can represent like qubit correlations. And in fact, we found one. So like to every like qubit state in this Kochen-Specker model before, like you associate like one vector lambda according to a certain distribution. Now we associate like two vectors, lambda 1 and lambda 2, that also have a certain distribution. But this distribution is simply, it's uniformly and independently like distributed, and the positive hemisphere is centered around like the quantum state V. So and then, okay, so it's what one can show that like for every possible POVM, like there is a response function given these two lambdas that produces an outcome, and this outcome exactly obeys like quantum statistics. And this works in principle for any POVM you can choose. And like based on this model, so if you believe me that this is true, then there is also like they can simulate like qubit prepare measure scenarios also with 2 bits of communication for all POVMs. In fact, they again start from some shared random vectors. They are again uniformly and independently distributed on the Bloch sphere, so like arbitrary directions in the Bloch sphere. And now if Alice selects the state she would like to send, she does the following. So she checks for both of these vectors if they lie in the correct hemisphere around V or not. So in this case, lambda 1 is already in the correct one, but lambda 2 is not. So what she would tell Bob is like to not flip lambda 1, to keep lambda 1, but to flip lambda 2. And this also requires 2 bits of communication, like 1 bit for each of these vectors. And if you check like the distribution of these 2 vectors after Bob flipped lambda 2, it's exactly like the distribution from the slide before. It's exactly like this model, like this ontological model of the qubit state that Alice would like to send. And if you believe me that this is a valid model, that something one can actually prove, then it follows that like everything you can achieve with a qubit in this prepare and measure scenario, you can like also achieve in this qubit protocol here. Yeah, all right. So this is the first part of my talk. And now this is about...
I have a question.
Yep.
So do you get back the Punervikan model from this thing, but as a special case or something like that?
So can you say again? I think maybe my laptop is not super loud. Speak a bit louder.
Yes, okay. So can you get back the like the Punervikan model as a special case of this one, of this protocol?
Yeah. Yeah, very good question. So there are some connections. So you don't get you get something very similar, yes. So it's not exactly the same, but there are some relations. So for instance, if you have a projective measurement, okay, to answer your question, it's something very similar, but it's strictly speaking not the same. But there are some relations. So for instance, what turns out, if you have like these two vectors, so there is a connection between like the models that we have, like the models that we introduced, these two lambda 1 and lambda 2, and the Koch-and-Specker model from before. In fact, if you kind of like take the sum of these vectors, so they are distributed exactly like in the Koch-and-Specker model before. So if you take the sum, so in this case, they would be like in the middle, or like the average. You take the middle point between lambda 1 and lambda 2, then it turns out that it's more likely that like this middle point is distributed somewhere close to V. And in fact, one can calculate that this is exactly the Koch-and-Specker model. So there are some relations. So for Bob, what he could do in this approach, if he has a projective measurement, he could like kind of take the sum of these two vectors, or like the average. He takes the middle point of these two vectors that he has, like lambda 1 and the flipped lambda 2. And then for a projective measurement, he checks if this middle point is like closer to the plus or to the minus of his projective measurement. And this would also work. And then you get something very similar to the Donut-Bacon model. Okay, so like in a nutshell, there are some relations. They are not completely obvious, but there are some relations. Yes.
Okay.
Okay. Yes. So then I go on. All right. So in the second part, like, so what you consider is like, so you can, like, this question of like how costly is it to simulate quantum correlations, you can in principle ask in every possible scenario. So like, for instance, you can also ask it for like in a Bell scenario where you have Alice and Bob and they share an entangled state. Like in this case, let's suppose they are like a two-qubit state. And if they like perform local measurements on it, they get, of course, certain correlations, like according to Born's rule. And the question is like, okay, like these correlations you can achieve here. Again, like Alice is free to measure what she wants and Bob is free to measure what he wants, and they don't have to know what the other person is measuring. How costly is it like to simulate these correlations? And of course, like one obvious constraint that we have here is that if you want to simulate everything just with like purely shared randomness, it's in general, or like for most states, not possible, because like they violate the Bell inequality, and that means like you cannot find the local hidden variable model. But probably, or what you can ask is if like you allow them to transmit some information, so some classical communication on top of these hidden variable models, on top of these hidden variables, can you then like simulate the statistics? And that's, I would say, like some like it's also like a kind of natural measure, like to quantify how non-local a state is. So for instance, if you have a state, and you can prove like all correlations can be simulated perfectly with just like one bit of communication, for instance, then it's arguably not that non-local as like a state where you can kind of show, suppose that you need like 100 bits of communication. So in that sense, it's I would say natural measure of like quantifying how non-local a state is. So okay, like what can we say about this problem? And one thing that we can show is that, or that one can show is that, like, if you consider a general two-qubit state and you would like to like simulate the statistics of arbitrary like local measurements on this two-qubit state, turns out all of these statistics for arbitrary qubit states and also arbitrary POVMs, so the most general class of POVMs, can be perfectly simulated with 2 bits of communication. And the idea is that, like, so Alice, she knows like what she would like to measure on her part of the entangled state. So she knows her measurement, and if she knows her measurement, she can calculate like the marginal probabilities for her outcomes, and she chooses one of these outcomes according to the marginal probabilities and outputs this. And given her outcome, she can kind of know, she can calculate like what is the state of Bob's qubit after she would get this outcome in a proper like quantum experiment. So if she properly performs her measurement on this part of the entangled state. And so this gives you a qubit state, and then she can like kind of use this qubit prepare and measure scenario to like send this state to Bob. And this is like all the information that he needs. So he has, it's indistinguishable if you like do this procedure and simulate it with a qubit prepare and measure scenario. So for Bob, like nothing changes. And actually, if you do the calculation, it's not hard to show that like this actually does its job. So what we conclude is like for arbitrary 2 qubit states, like all measurements can be always simulated with just 2 bits of communication, as long as you have like shared randomness. All right, but so sometimes, so you can ask, okay, like can you do better than that? So what is so this is like an upper bound, kind of like 2 bits is always sufficient. Can we do sometimes better? And the answer is yes. So for instance, like what Toner and Bacon, and also in this like 2003 paper proved, is that like when they share a singlet, so like you have the state 0, 1, minus 1, 0, and you perform arbitrary projective measurements in this case, then like if you do so, you get certain correlations for arbitrary like X and Y, and all of the statistics can be perfectly simulated with like local hidden variables plus 1 bit of classical communication. And like unsurprisingly, so they have an explicit protocol. It's very similar to this protocol in the prepare and measure scenario. There's some small changes. So like you start from, I don't go step by step through the full protocol, just so you like the idea. So you start again from like some shared random vectors, and like Alice checks which of these 2 vectors is closer to the axis she would like to measure. Then she tells Bob to use this one, and Alice outputs like according to if this is closer to plus or minus. And also Bob, like when he chooses his projective measurement, he can check if it's closer to plus or minus and outputs accordingly. And again, like if you average over all of these like shared random vectors that are like in principle arbitrary on the Bloch sphere, they on average they get exactly the same as if they perform actual measurements on the like singlet. So if you solve the integral, you average over lambda 1, lambda 2, you get that on average the probabilities for A, B are exactly the same as in the quantum case. So this can be done with just 1 bit of communication. So you can ask, okay, like, so singlet might be a special case. Can you also do it for, how does it look for arbitrary states? So in principle, you can ask this question for arbitrary states and arbitrary measurements. So what we knew is that like the maximally entangled state, 1 bit is sufficient. Turns also out that if the state is either weakly entangled, then also 1 bit is sufficient. And there's also like some recent projects by like the group of Valerius Garani. There's numerical evidence that like 1 bit is sufficient for arbitrary 2-qubit states, as long as projective measurements are considered. And like if you have general POVMs, like the best we currently know are these 2 bits, but it could be also better. It could be also like 1 bit, but we just have not found like the correct protocol yet. So I would say for 2-qubit states, like it's quite well known, but kind of surprisingly, if you go to higher dimensions, so for instance, Alice and Bob, they share like n Bell states. They perform like so n maximally entangled Bell states. Then they perform like a joint measurement on their part, and also Bob performs a joint measurement on his part. We don't know how to simulate this, for instance, but we know that it has to be a lot. So there's like it's at least exponential in the number of Bell states. But this is only a lower bound, and it could be even infinite in principle. So we don't know if like these scenarios can be simulated with a finite protocol or not. And I think it's quite surprising, and it's also like still an open problem. Yeah. All right. Okay, so this is a summary of these results, but of course you can also ask it for multipartite entangled states or like anything, sequential scenarios, like anything you want in the end. And like for many of these things, like if you want an exact simulation, it's not super well known how to do that. Okay, good. That was still have some time. And yeah, so if you have questions, please just feel free to interrupt me. So otherwise, like I would like to, so like this Toner-Bacon model, for instance, I think it's from a foundational perspective quite nice. I would also say it's a like natural question, but on top of that, like it also has some like natural applications, I would say, or in fact, it's connected to other concepts in quantum information theory. So for instance, it's connected to Werner's model, or it's also connected to other models that we to general local hidden variable models we have in quantum information. So let me explain. So when Alice and Bob, they perform a Bell experiment, of course, like you can violate Bell inequality up to some value. But in reality, like you might also want to consider like scenarios where like you have some noise in the sources. So like you don't have a perfect singlet, but you have sometimes some noise in the source, and that might affect like your potential to violate the Bell inequality. So if you have a little bit of noise, your violation goes down, and at some point you might reach the local bound, and then you are unable to violate the Bell inequality. And as like what was quite an important insight is this work by Werner, that if you have like too much noise, for the qubit case, it's like 50%. So in 50% of singlet and 50% of white noise. So that means like your source in half of the cases, it actually does what it's supposed to do and like gives you a singlet. In the other half of the cases, just gives you some like random state, let's say. And so the question is, with such a source, can you still violate the Bell inequality or not? And the answer is that you cannot, because like all correlations you can achieve by measuring such a state, you can like perfectly write into this form some like response for Alice and some response for Bob. So this defines you like a local hidden variable model. Therefore, you cannot violate a Bell inequality in this setting. Okay, and this is like quite known work from 1989 by Renner and Werner, that some entangled states do not violate a Bell inequality. But okay, why am I showing you this? I'm showing you because it's like connected to this Toner-Bacon model. So for instance, so let's suppose you have like Alice and Bob, and they would like to implement this Toner-Bacon model. So like Alice would like to send this 1 bit of information to Bob. But now we are interested in constructing a local hidden variable model. So Alice is not allowed to send this bit. And okay, let's see how far we can still go with that. So one idea here is, so Alice does not send a bit, but apart from that, she just proceeds with her protocol. And now Bob, he doesn't have the information of like which of these two vectors to choose, like lambda 1 or lambda 2. But okay, they are just two vectors, so he can like kind of think, okay, maybe I just guess which is the correct one. And in half of the cases, he will make the correct guess, and then they actually perform the protocol and they produce singlet correlations. And then the other half of the cases, he will make a wrong guess. And then like it turns out that he has an uncorrelated outcome, like he has something uncorrelated to Alice. But what it does is simply like it defines you, like in 50% you get the singlet, and in the other 50% you get some uncorrelated results, so white noise. And it basically, like in this way, you can get Werner's model from the Toner-Bacon model, which I think is somewhere interesting. But okay, yeah, like something similar, like you can also do, like, so when you have the Bell experiment, and in particular when you do it with photons, and there are some chances that you might lose the photon. So like especially when you have your source and then like Alice is far away, or like the two people are far away from the source, there's some chance that like the photon gets lost on the way. And the question is, okay, if you lose like just some small fraction of the photons, you can still violate the Bell inequality, like your violation goes down a bit, but it's not a big problem. But if you lose too many photons, it might be a problem. And then you can also ask, like, how many photons can you lose before you don't violate any Bell inequality anymore? And that was like one like, the first work here was by Jizong and Jizong. They are two brothers. They construct like a local hidden variable model that is exploiting this losses, these detection loophole. And what they can prove is like if Alice loses half of their photons, and like then they cannot violate the Bell inequality, even if Bob has the perfect detector, so he never loses his particle. And also this one turns out to be connected to the Toner-Bacon model. I don't go into the details of this protocol here, but I show you like some intuition how you can get it from this Toner-Bacon model. So also here, like Alice and Bob, they would like to perform this protocol with 1 bit, but now we want to construct this like we don't allow them to send a message because we want to construct a local hidden variable model, and then like we don't allow Alice to send the message, but kind of we agree, Alice and Bob agree beforehand the message was 1. And then like if Alice knows, okay, under these situations, for these like constellation of lambda 1 and lambda 2 and my choice of the measurement basis, I would have actually liked to send the 1. Then she just proceeds with her output and outputs A with plus or minus 1. And also Bob simply assumes the message was 1. Okay, now in this picture it's 2, but okay, never mind, I guess. Fine. And then like he proceeds with that. But if Alice kind of like sees that she would like to send the other message, she just claims that the photon was lost. And if like Alice like actually wanted to send the correct message, then it's fine, and they like successfully perform the Toner-Bacon model. But if like Alice wanted to send the other message, she just claims it was lost. This will happen in 50% of the cases. And so that's a nice way how like these Toner-Bacon and this Jizong model is connected. So in general, I think it's fair to say like these methods you can use there, you can also use like for construction of like local hidden variable models when you want to know if a certain state violates the Bell inequality or not. All right, with that, I'm coming to an end of my talk. So like we introduced these classical simulation. And like we could, like for qubits, for instance, like everything can be done with 2 bits. This gives you also like an important upper bound on like the quantum to classical advantage in these scenarios. But there are many open questions as well. So like for a qubit, we know quite well. But basically, if you go to other scenarios, like when you go to higher dimensions and you replace a qubit with a qubit, then we don't really know if it's even finite. So there's not really a known protocol. And also, like, if Alice and Bob, they share some entanglements in addition, or like we go to 3 parties, like they have like a G at Z state, we know some partial results, but in general there are many open problems, and yeah, we don't really know. And I think that's quite surprising, given that, at least in my, like, these are questions that people ask like since 2000, and there's still a lot of things to do, I guess. All right, so thanks a lot for your attention. So that was my talk.
Thank you, Martin, for your nice and well-explained talk. Now we can take some questions.
Hello,
Can I
Martin.
ask one question?
Oh, okay. Somda, you go first.
Okay. Okay, so when you talk about like for correlation simulation, so then as you said, the cost of communication could be a measure of how non-local the correlations are.
Yep.
And also Bell violation is a measure of how non-local the correlation is, right? And
yes,
somehow for the one class, you kind of get some kind of compatibility between these two measures, right? Because
yes,
one could show that if there is some like depolarizing noise, it is kind of explainable in that sense. So could you comment on some other kind of non-locality measures, for example, like the geometric measure of non-locality or something like that? Could you also make that thing related to the communication cost in some way for some other class of states, of course?
yeah. Yeah, and it's a very good question. Thanks a lot. I never thought so much about it. Okay, what you can say, for instance, like if you consider the maximal violation of a Bell inequality, and like you know, for instance, you have your singlet, and suppose you only consider like, oh yeah, you suppose you have a singlet, and you know, like all correlations can be simulated with like 1 bit. And then like you can ask, okay, for a given Bell inequality, what is the best you can achieve with 1 bit of communication from Alice to Bob? And then you know that like what you can achieve with a singlet cannot be beyond that. So for instance, okay, for CHSH, like if Alice is allowed to send 1 bit to Bob, she can just communicate her input. And this is kind of trivial. They can reach the maximal like algebraic bound. But if you have several settings, this might give you something, but in practice, I don't know how well it does. But okay, so there are some connections, at least if you consider like the maximal violation of a Bell inequality for a given state. How well it is connected to other things, I don't know so well, to be honest.
Okay. Thanks.
Hi, Martin. Nice talk. So I just wanted to ask probably a stupid question. So can we say that when we formulate Bell non-locality in a prepare and measure scenario, so in that case here, it is a proof of case contextuality?
So can you say it again? Like when you have?
So when you interpret the Bell scenario as a prepare and measure scenario, right? In that case, does it constitute a proof of case contextuality?
Okay, if you interpret the Bell scenario as, do you mean?
What I mean is just the correlation. You know, you have the Bell inequality, right? Now the violation of the Bell inequality would constitute a proof of case contextuality when you interpret
Mm-hmm.
it in a prepare and measure scenario.
Mm-hmm.
So is it, can we say that? Like some kind of, the way you are simulating the correlations, it's always you construct a hidden variable theory that is out, and then hidden variable theory has some kind, and using that hidden variable theory, how much, and in a communication, when you consider communication cost, it is a prepare and measure scenario to some extent, we can say, no? So
okay. Yeah, I would say like as long as you have like some, I'm not sure if it's like somehow connected to the simulation. Maybe I would say like as long as we have some advantage in a prepare and measure scenario, you need, I guess, some kind of contextuality, at least like generalized contextuality. But it's yeah, I guess there are some connections.
Because there is this paper that I remember by Tobias Fritz, where he discussed the structure of the temporal CHSH correlations. So there he made an argument was saying, okay, these expectation values of the tensor product that reflected as anti-commutation between expectation value of the anti-commutation between two observables. So I was thinking that, okay, in that sense, like whether your thing has a connection to like how much you can, simulate is quantum mechanically is restrict, or, classically also it probably would be to restricted in the sense that whether you have a type of this anti-commutation relationship, you have something analogous to anti-commutation relationship in the classical thing, which we know that if we think compatible case, it does not arise.
Okay. Yeah, could be.
Okay. Anyway, so probably we can discuss later.
Yes.
Yes. We can take a few more questions. For example, Marinda, can you unmute yourself? And
yeah, Martin, you are discussing some open question at the end, no? So there is this. Yeah, so this simulating higher dimensional systems. So as you have discussed in your paper, when this prepare measure scenario we try to simulate, that can be thought as some hidden variable model simulation protocol. So the communication and the shared variable is the hidden variable or ontological variable. So in 2012, Montina has a very interesting result. He has shown that this epistemic view of quantum state, that was the title of his paper, epistemic view of quantum states and communication complexity of quantum channel.
Yes.
What he proves there, that if a finite communication model exists, then it corresponds that there exists a maximally shy epistemic model.
Yes.
And in a sense, he also argued, try to argue that it is the opposite is also false. So now from Maroni, Barrett, then what is called this Liffard, from their theorems we know already for C3 onwards, no maximally shy epistemic model cannot be constructed.
Yeah.
Doesn't it hint towards that a finite communication model will not be possible for C3 onwards?
Yeah, that's a hint, yes. But it's also, so far I have not seen a proof that puts everything together, like.
Yeah. He also says, he, in a sense, he argued, he doesn't say it is a full concrete proof, but probably it seems that this makes life complicated in C3 onwards, this shy epistemic, because shy now become the part of reality. It is not a classical variable kind of things. We cannot think like that. That will make our life complicated to simulate it classical.
Yes. Yes, yeah, definitely. Like also, I think like if you want to simulate like these simulation scenarios, they are always directly linked to these like models. And the question is, can you come up with a model? Yeah, so it's about disproving that. But it's also, yeah, I think it, okay, like so far I have not seen like really like a proof that puts everything together. I think that would be very, very good to do that. Yes.
Okay, fine. Thank you.
Yeah, Rahul, you can unmute yourself and ask him directly.
Okay. My question is also related to this scheme of trying to come up with a measure of non-locality. So the way you were doing it, you were saying we are allowing for some amount of communication. So from the Bell's theorem perspective, this would correspond to relaxing some amount of no signaling condition, right?
Yes.
For singlet, you'd have to say that okay, 1 bit is not only sufficient, but it's also like necessary. It's a minimum cost. And for any arbitrary entangled 2-qubit state, you'd also have to say that if we can come up with a LHV model which can do it in only 1 C-bit of communication, then we'll say okay, any 2-qubit entangled state has the same amount of non-locality as let's say the singlet state.
Yeah, that's a very good point. No, okay, so like it turns out like for singlet, you have a proof that like a singlet has no local content. So
right.
For instance, like if you ask, sorry, if you ask like your protocol, like so there is a Stoner-Wakeling protocol that sends like always 1 bit. You can ask, okay, is it for instance possible that you send like in 50% of the rounds you send 1 bit, and in the other half you don't send anything? And then this would contradict the fact that like the qubit, the singlet has no local content. That was kind of imply a local content. But you can have something like this for for non-maximally entangled qubit states. So there are some protocols that requires 1 bit in the worst case, but like for instance, like some very weakly entangled 2-qubit states, you can simulate it with like 1 bit only in 10% of the rounds, and in 90% of the rounds you don't have to send anything. So from this perspective, I would say like weakly entangled 2-qubit states are less non-local according to the simulation cost.
Right, that makes sense because the product state shouldn't that doesn't have an entanglement, so the cost should be 0 for that.
Exactly.
And like equivalently, we could relax either of the other 2 assumptions of Bell's theorem. So there is a result of like Branchiard where he says you have to relax the outcome independence condition for 1 bit. There's a statistical measure like that is defined for that, and you need to so relax 1 bit of outcome dependence to simulate the singlet. So so you can also do that for relaxing measurement dependence. So my question is like going to so we should be able to define the measure of non-locality by relaxing those 2 conditions as well, first of all.
I guess, yeah, I mean, I guess it's a valid measure.
My point is like I feel like it would be easier to like go those routes to like particularly for this defining of like a measure of non-locality because for you have to what you have to do here is like you have to sample the correct lambdas and then you have to define okay what is the distribution required for a particular amount of entanglement, and you have to then see how much amount of cost you would require. So rather than doing that, let's say we go to the like measurement dependence route and we say we come up with a model which can do it which can simulate any 2-qubit entangled states and we have some function for like we have some map that maps it to how much entanglement corresponds to how much non-locality. Is that possible? Do you think that's a good way to go about it?
Yeah, it sounds reasonable. I'm not so sure about like what is done there and what not. But yeah, no, sounds reasonable.
Okay. Thank you for the talk.
Thanks.
Okay, thank you, Martin. Thanks for the nice talks. Now we can end here. It is almost more than 1 hour. Okay, once again, thanks to everyone. We are ending this meeting right now.